Welcome to the video for C2.2.4. So this is part B. So last lesson we looked at drawing dot and cross diagrams. Today we're going to look at the properties of ionic compounds. So before we start, we need to think about which of these structures is able to conduct electricity. So think about what electricity is. So if you put your physics hat on, think about what electricity is and look at those diagrams and see if they have the potential to conduct electricity. And then think about what they've all got in common, the ones that do conduct electricity. So pause the video and write your answers down now. Okay, so hopefully you've come up with the idea that C and E will conduct electricity and A, B and D won't. So we've got to think about what electricity is. So electricity is a movement of charged particles. So if we look at A and D, there's no charged particles there that can move. So they definitely can't conduct electricity because there's no charged particles. In B, that's a solid particle diagram. So even though there's charged particles, none of those charged particles can move because they're in a solid formation. So they just vibrate about a fixed position. They won't move past each other. So in C, so C shows something dissolved in water. So you've got charged particles there, you've got plus and minus that's dissolved. So because it's in solution and dissolved, it can move. And E is a diagram of a metal. So you've got the positive cations and then you've got the delocalized electrons that can move. So both C and E have got charged particles that can move and therefore they can conduct electricity. So as it says on the slide, what they've got in common is they contain charged particles that are free to move. So we'll look at this in a bit more detail now. So our learning objectives for today, you need to be able to describe the structure and bonding in ionic compounds, which is leads on from the last lesson. And also you need to be able to describe the limitations of different models of ionic compounds. So if we look at our structure of ionic compounds, so an ionic compound has millions and millions of ions which are just in a regular repeating arrangement called a giant lattice structure. So you've got positive and negative ions. So in this case, that could be something like sodium chloride, where you've got one positive ion for every one negative ion. And the positive ions we call cations and the negative ions we call anions. And because they're opposite charges, you've got a strong electrostatic attraction between the oppositely charged ions. So ionic bonds tend to be strong. And that structure affects the properties of the ionic compound. So we need to be able to link the structure and the properties. Now, before we do that, we're going to look at two different models or ways of representing ionic bonding. So you can have the space filling model, where it's like a 3D structure, but that you can't see any spaces in between them. Or you can have the ball and stick, which is the molecular models that we use in class that are just connected to show alternating patterns of positive and negative ions repeating in a lattice. So if we look at our space filling model, it's good because it shows that ions are close together. And so in real life, if we could zoom in and see our ionic compound, the ions would be really close together. There's no space in between them because it's a solid. However, because there's no space between them, it's difficult to see the structure. So the structure's a bit unclear. I can kind of see that it alternates positive and negative, but you can't see the details of the structure in terms of how many ions are surrounding one particular ion. The ball and stick model is better in that it shows the alternating arrangement clearly. So you can clearly see that it's alternating between positive and negative ions. And if I look at that green one in the middle, I can clearly see that I've got 1, 2, 3, 4, 5, 6 of the oppositely charged ions surrounding it, which I couldn't see in the space filling model. However, it's got bonds between the ions, which is good because there are bonds, but those sticks kind of imply that bonds are physical objects, and they're not. Okay, so it's just a force of attraction. It also doesn't show them close enough. So in order to show the arrangement clearly, they're quite far apart. But in reality, there's no space in between the ions. So from that point of view, the ball and stick model isn't very good. So we need to be able to make links between the structure of ionic compounds and the properties of ionic compounds. So there's four properties that we need to be able to explain. So ionic compounds always have high melting points, and that's because there's a strong force of attraction between the oppositely charged ions. So you need to put in a lot of energy to rip the positive and negative ions apart from each other because they're very strongly attracted to each other. As a solid, it doesn't conduct electricity because as a solid, those ions, even though it's got charged particles, the ions can't move because they just vibrate about a fixed position. So because the ions can't move, there's no mobile charged particle, so it doesn't conduct electricity. However, if you take your ionic compound and dissolve it in water, or you melt it so it's a liquid, then the ions can move, and so it becomes able to conduct electricity. And then the last property that we need to be able to explain is that ionic compounds are always brittle, which means if you hit them, they will fall apart easily. And that's because if you think about the repeating patterns of oppositely charged ions, if you hit that with a force, then ions with the same charge will be forced next to each other. And if you've got two positives next to each other, they're going to push apart. And if you've got two negatives next to each other, they're going to push apart. So because like charges repel each other, if you hit it with a force, the like charges tend to line up, and then they will repel each other and be forced apart. Okay, so that's the last of the new information. So what you need to do now is there's a separate video that has me explaining how I would answer this question. So this question is asking me to draw dot and cross diagrams for when magnesium chloride is formed, and also to make links between the properties and its bonding and structure, which is what we've just discussed. So it's using what we've discussed today and in the previous lesson. So if you watch the other video on that and write down exactly the same notes as I have done, and then you need to have a go at this student question. Okay, so it's very similar to the previous question, so you need to use the same ideas and the same approach. And then what you need to do is take a photo of your answer and email it to me, and then I can send you the marking back via email. Okay, so the last thing you need to do is just look at the information in this table, and there are two ionic substances in that table, and I want you to look at the properties of its melting and boiling point and whether it conducts electricity as a solid or liquid or solution, and decide which two of those are ionic compounds. So pause the video. Okay, so hopefully you've come up with the idea that C is an ionic compound because it's got a high melting and boiling point. It doesn't conduct electricity as a solid, but it does conduct electricity when it's liquid or solution. And D is the same, although it doesn't conduct as a solution because it's insoluble. So if we look at A, it conducts electricity as a solid, so that can't be an ionic compound. If we look at B, it doesn't conduct as a liquid or solution, so it can't be ionic. And if you look at E and F, so E's got a very low melting point to start with, as B did, but both E and F do not conduct electricity as a liquid, so it can't be ionic. Okay, thank you for listening. See you next time.